So yesterday, actually, we found out the mean stress in the muscle first, and then the individual muscle forces in muscle biceps, in muscle brachioradialis and brachialis. So these three muscles we have found out, okay, based on the simple free body diagram of the elbow joint. Now remember, there were some assumptions in this whole simplified problem. So here the individual, if I highlight the individual joint reaction forces of both the humeroradial and humeroarticular articulation, this has not been calculated. Okay, once you have the forces of the muscles and of course the external loads, you can easily calculate the joint reaction force at the elbow joint, at the joint through which the axis A passes. But we have to remember the fact that we did not consider the humeroradial and humeroulnar articulations separately. Okay, so we assume that these two bones carry an equal share of the limb weight. Okay, so we have basically assumed it to be same bone, so that each of which will carry half of its own weight. But now we will actually go deep inside the problem and try to find out individually what are the humeroradial joint reaction force and what is the contribution of humeroulnar joint reaction force. Okay, so we designate this humeroradial joint reaction force as RR. Okay. So we don't know what is the portion, a percentage of the external load that is being carried by the forearm is carried by the humeroradial articulation. Okay, but we assume that half of the weight of the forearm is being carried by the radial bone. Again, we take into consideration the biceps brachii, so biceps brachioradialis. So these two muscles are acting on the radius. Very importantly, and based on which we will calculate the reaction force. But very important, the ligament forces for the first stage or the first part of the problem is not taken into consideration, and it will be later taken into consideration. Okay, so we start with the problem shall be ignored for the first stage of the calculation. Okay. So if I look into the left-hand side, the free body diagram, as you can see, forces acting on the radius. You have the biceps, you have the brachioradialis. This is the external load that I'm carrying. We don't know what is the exact amount or what is the exact percentage of the total load. We only assume that half of the limb weight is being carried by the bone radius. And of course, there would be a joint reaction force inclined at an angle alpha. Okay. So obviously, the next step is applying the principle. Moment applied by the loading is equal to the moment applied by the muscle about the joint axis A. Okay. So what are the muscles? We have the muscles biceps, moment created by biceps, and moment created by brachioradialis. These two muscles only when we consider the radius. Obviously, the same set of calculations, you have to calculate the moment arm. You have already calculated the forces in the muscle. So we get the bicep muscle, moment of the bicep muscle. Similarly, brachioradialis, you can calculate the moment. Okay. Now, half of the limb weight is this, according to the basic data that is given. And the moment that it creates about the joint axis, of course, you know the location of the CG. So you multiply with the moment arm and you get 2.08 Newton meter as the moment applied by half of the limb weight. Okay. And the only unknown in this equation is WR, that is the amount of weight carried by the forearm. For this case, amount of weight carried by the bone radius, which is unknown. So WR multiplied by the distance at which it is acting, so that is given 0.35, plus the moment created by the limb weight will be equal to the muscle moment applied by the muscle about the joint axis A, from which we can calculate the weight carried by the radius bone, which is 155 Newton. Okay. Earlier we had calculated, it was given that it is about 249. So 249 minus the 155, that is 94, should be carried by the ulna. Okay, total weight was given as 249. The remaining part, that is 94 Newton, is now carried by the ulna. We are trying to separate the problem, the contribution of the radius bone and the contribution of the ulnar bone in the mechanics of the elbow joint system. So now, once we have this amount of external weight determined, carried by the radius bone, we can use the equation of statics, because this thing is in static equilibrium, and we can resolve it horizontally and vertically, the two equations 11.1 and 11.2 respectively. Okay, so if you rearrange, you can easily find out the angle alpha, which is this. You can see the angle at which the RR is inclined, and this angle is with the, you can see as shown in the figure. So once you have the alpha, you can put the value and you can find out RR, the joint reaction force, which comes out to be 1013 Newton as per the calculation. Okay. Since you have this angle 17.2, you can actually calculate the normal component and the tangential component, which is actually in form of a transverse sliding force. Okay, so if I refer to the figure here, 11.21, you can see very clearly this is a sagittal view. Okay, I hope everybody understands what is a sagittal view. So there is a plane which is starting from the front going to the back. Okay, Just let me prompt here. Yeah. Are you all aware of what is the sagittal plane is? Hello?
Yes, sir.
Yes, sir.
Yes,
Yeah.
sir.
Unless you understand the plane orientation of the plane, it will be difficult for you to understand the mechanics. Because this figure, whatever I'm showing you, or you can see it yourself in the document, it will be difficult for you to understand the direction of the force and what it is physically causing. Okay, so I'm going back to the presentation once again. So we have when we have this sagittal sectional view, then you can see that this resultant force, the humeroradial reaction force, it is inclined at 17.2 degrees. And then we can actually resolve this RR into two components. One is the normal component, and another is the sagittal component, another is the transverse component or the tangential component. This transverse component is actually a force, is a sliding force that is tending to separate the two bones. Okay, so it is trying to separate the radius from the capitulum. Okay, and it is quite a large force. As you can see here, RT is about 700 newtons, 689 newton more precisely. So this is quite a force which is a sliding force in the transverse plane, and this would cause the radius to separate from the capitulum. Okay. However, what does that mean? Separation. Separation. It will be pulled sidewise across the capitulum. So the radial head, the head of the radius bone, there is a tendency due to this force to pull the radius head sidewise, and according to the direction you can see that it is actually moving outwards radially. It is moving laterally outwards. There is the tendency to pull it sidewise across the capitulum head. However, in reality, as you all know, that this is not actually the case. It is never sliding outwards. So something must actually act to keep this whole thing in position. Okay, but before I move on to the critical part, let me tell you that there is always at the contact point, there is a friction coefficient, however small it may be. So interface at the contact, if we consider the friction coefficient to be very low value, mostly these values have been, there's been a lot of investigation. So you can see mu is equal to 0.02 if we take, then the frictional force would be mu into the normal component. So 744 multiplied by the frictional coefficient would give you a 15 Newton force, which can be designated as a frictional force at the contact point. So if we subtract from 689 this 15 newtons, we are left with 674. And this 674 is the remaining force that may cause the radial head to slide sidewise from the capitulum. However, as I told you, this never occurs, and there is some force which is actually trying to neutralize this remaining force of 674. For example, for this case, based on this data, we are saying 674 Newton. So this is basically taken up by the ligamentous system. Okay, there is a ligament to hold or resist this force and keep the radial head in position, articulating in the capitula. Okay, so this is being taken up by the ligamentous system, which restores the radial contact to equilibrium. This is very, very important. So I hope you now understand physically that what is the contribution of the ligament in the whole musculoskeletal system. It basically stabilizes. It is a passive force that stabilizes by connecting two bones. Okay, so here also the radius is being connected or being held together with the humerus through a ligamentous system, and they stabilize the system in such a way that it restores radial contact with the capitulum and thereby restores equilibrium of the system. Now the force imposed, so we have, if you study a little bit more, you can see if this is 17.2 degrees. If we look into the figure 11.21, a little bit carefully, we can determine the angles, actually, different angles. So if this is 17.2, this is 42.8. Together it makes 60 degrees. Okay, and this is 30. So if this is 30, this angle is also 30. And this whole angle is 90 between RT and RN. So because they are two orthogonal components. So we have basically all the angles now. So this is 60, this is 30, this is 30, and this is 30. Okay. Now as you can see that how is this force of the ligamentous system act? So it will act to oppose the tangential component, acting almost along the similar orientation. So here also FL, the ligamentous force system, should act at an angle 30 degrees, as you can see. And this is basically, we have the data that it acts at 0.08 meters from the joint axis. So we fix up the point of application and the line of action of the ligamentous force, and we again take up the equilibrium of the system. Okay, so you can see the combined component. So what happens is that the combined component of the ligamentous system will impose a moment. So the moment imposed upon the radius by the ligamentous system is of the magnitude 52 Newton meters. Okay, so which is calculated from this moment arm 0.08. When we resolve this angle cos 30 degrees multiplied by the force, which is 674. 674 comes out because 689 minus the frictional force, that is 15 Newton. So if we subtract 15 newtons from 689, it gives you 674, the remainder force, which is being sort of resisted by the ligamentous system. So now we have the moment imposed by the ligamentous system. So the moment basically opposes the flexion and so decreases the load which can be carried. Okay, so previously we had calculated, if I go back, what is the load being carried by the radius? It is 155 Newton. You can see here highlighted WR is equal to 155 Newton. So previously a load of 155 Newton at a moment arm of 0.35 was being carried, giving rise to a moment of 54.25 Newton meters. Okay. Now, out of which you see, once we apply the or consider the ligament or include the ligamental force, this is actually reducing or helping the system to lessen the weight being carried. Okay, so if we subtract 52 newtons from 54.25, the moment created by the external force, then we are left with 2.25 Newton meter load to be carried. So the load to be carried, if we just divide it with the moment term, it comes out to be 6.425 Newton. So when we are actually considering the ligamentous system in action, it results in less weight being carried by the radius. Okay, effectively, the radius is now carrying 6.425 Newton because we have an extra ligamentous force that is stabilizing the joint. So, we have induced the ligament in the system, an extra element in the system, which was not considered earlier, remember. So the resultant elbow joint, the resultant force at the elbow joint, RR, now needs to be recalculated based on this new system or upgraded system that includes the ligament in the calculation. Okay. Now the normal component Rn remains unchanged, so that is basically equal to 744 Newton and acting at a 60 degree to the humeral axis. So we just take up, revisit the force diagram, vector diagram, and you can see that 744 is the normal component. 15 Newton is the basically the frictional force component, so we keep that. So this is the RT is 15 newtons. So this is absorbed by the RT. So if it is trying to move this way or that way, the direction will change. But this is the tangential force now, which is acting at this point of contact, but balancing the frictional force. Okay. So based on these two revised force components, we can calculate RR as 745 acting at an angle 58.75. So that can be easily calculated. You can see here subsequently. Once we have these two components, Rn and Rt, the rest can be easily calculated. Okay. So the new joint reaction force, considering the ligaments, has now been determined. Okay, but remember, this is still a simplified analysis. A more sophisticated examination of the structure. Okay, when we say more sophisticated examination of structure, is then it means that we are actually taking into consideration the intricacy of the geometry at the humeroradial contact, and of course the bones connected to that. So more sophisticated examination of the structure would also take into account the muscles passing through the forearm. So apart from the structure, we will also take up the muscles that will be passing in the forearm, and which, to whatever extent, be it minor, be it major, will have some influence in the calculation of the joint reaction force. So suppose in the forearm we are executing some grasping action of the hand. So that is basically a grasping action of the hand. Basically, if you consider the role that includes the grasping action of the hand and stabilize, basically it it results in stabilization of the hand at the wrist. Even if it is wrist, this muscle actually originates from, say, the epicondyle, from the humerus. It has connection with the humerus, so the muscles are not restricted in the neighborhood of the wrist. It actually originates from the epicondyle of the humerus, and they pass through the elbow joint and then attaches somewhere, and it contributes towards, say, a grasping action of the hand and maybe wrist. But it compresses, it has its contribution on the elbow joint. Okay, so whatever small be its contribution, it will have some contribution in the mechanics of the elbow joint. So therefore, the effect of moving the RR, that is the humeroradial joint reaction force, more into the line with the radius. So basically it will compress the elbow joint, and this will actually result in moving the joint reaction force more into the line with the radius, so that it will not normally try to sublux. So the word sublux here means coming out of the socket. Okay, subluxation word is a clinical word, and it means that the tendency to come out, say, the radial head being forced out of the capitulum, so that separation doesn't occur. Okay, so by somehow the musculoskeletal system is designed in such a way that it will try to restore equilibrium of the structure and thereby ensure contact of the humeral head with the capitulum. Okay, so the radial force would, the humeroradial joint reaction force would be more in line with the radius, so that it will not normally try to sublux anteriorly, so it doesn't come out anteriorly. That is what it is suggesting. All the calculations and the mechanics is pointing out towards the fact that the system, musculoskeletal system, is trying to hold, is designed in such a way that it will hold the system and the bones in position. So therefore, there is a small correction in the calculation which you can easily follow. So please go through this calculation. That in view of the procedure, in the above procedure to calculate the ligamentous forces, the load supported by the ulna must be also modified. This has so far been assumed to be equal to 94 newtons. That is the remaining force from, as you had calculated, 155 subtracted from 249 would give you 94. So this is the moment, the revised moment would be now this plus the 55, 52, which is the moment produced by the ligament. So this is the revised moment of the ulnar force, and the corresponding load for the ulnar force would be 242.6. So this is divided by 0.35. Okay. So this is basically the load being carried by the ulna, considering the ligamentous system. Okay. The next, we will actually take up the humero-ulnar joint reaction force, which is designated by RU. Okay. So once we have the contribution of the external load 242.6 Newton, the half of the limb weight 13 Newton. In this system, the ulnar system, the forces acting in the ulnar system, as you can see here, is the ligament here at an angle. We have the force of the muscle force of the brachialis muscle, FBR, okay, which is 1020 Newton here. So orientation is given, and the RU, the joint reaction force of the humero-ulnar reaction force, is acting at an angle alpha, it is assumed. So we basically calculate similar manner, resolve vertically and horizontally. We calculate alpha, the direction of the reaction force, and then we can easily calculate the RU, okay, based on that. So this is the RU calculation. RU is equal to 1251, the magnitude of the reaction force. Now we have determined both the joint reaction forces. They are calculated. And once we have determined these two, the forces acting on the distal humerus can also be determined. Okay. So if you take the humerus separately, so you have the axial force, the two components, RR sine alpha and RU sine beta. So the axial load on the distal humerus comes out to be 1634. Now this axial load on the distal humerus is quite high, being more than twice the body weight. Okay. See, this is very, very high. Okay. Now the cross-sectional area of the cortical bone in the humeral shaft is about, mean cross-sectional area is 200 millimeters square. So the mean compressive stress comes out to be about 8.17 MPa. This stress is low compared with the compressive limit of the elastic behavior, so the strength of the bone, and that is about 86.4 MPa. This is a reference. So you can see how much the bone, the strong humerus bone, can sustain as far as stresses generated within the bone is concerned. Okay, so this is quite a high load, as already mentioned, that this is more than twice the body weight, but it is being carried very easily by the humerus bone, which has an average cross-sectional area of 200 millimeters square. Okay, so this is a very important calculation, which I would recommend all of you to go through the calculations very minutely. Okay, you solve this problem yourself, then only you will understand.